Today, we're going to learn about inductors and circuits. The things we take for granted in our daily lives, such as using our cell phones to send a text, tuning our car's radio to a particular station, or even using the GPS in our phones and cars to navigate, all rely on being able to send and receive electromagnetic signals that oscillate at well-defined frequencies. These oscillations are generated and detected by a simple circuit consisting of an inductor and a capacitor. This simple circuit is called an LC circuit. An LC circuit consists of an inductor in series with a capacitor and a switch. Initially, the switch is open, the charge on the capacitor is Q0, and the current is 0. At time t equals 0, the switch is closed. Given the inductance of the inductor L and the capacitance of the capacitor C, what is the charge on the capacitor's plates and the current in the circuit as a function of time after the switch has been closed? To answer this question, we'll need to rely on Kirchhoff's voltage law to allow us to write an equation that governs the charge on the plates of the capacitor and ultimately the current flowing in an LC circuit. Let's go ahead and draw our circuit. We have an inductor, and this inductor is in series with a capacitor and a switch. The inductor has inductance L, the capacitor has capacitance C, and at time t equals 0, the charge on the capacitor's plates is Q0, and the current in the circuit is equal to 0. Let's label a couple of points in our circuit in between the capacitor and the inductor. We will label this point A and this point B. Now, since the capacitor is initially fully charged, let's indicate the polarization of the charges on the capacitor's plates. We will have the positive charges being on the upper plate of the capacitor, the negative charges on the lower plate of the capacitor, and the uniform electric field is in between the plates of the capacitors, and I'll label that electric field as E. Now remember, that electric field stores electric potential energy, and it's that electric potential energy that is ultimately going to allow us to drive a current in this circuit. At time t equals 0, let's close the switch. When we close the switch, that allows current to flow in the circuit. Now, the source of this current is from the potential difference established between the plates of the capacitors. The capacitor donates its charge. Let's indicate that the current is equal to the time rate of change of charge. Now, since the source of the charge is from the charges that are removed from the capacitor's plates, this is going to have to be a minus sign indicating the removal of that charge. So here is our current as a time rate of change of charge. Now, as current moves through the inductor, we know that it will establish a magnetic field within the inductor. This magnetic field in the inductor stores magnetic potential energy. And this combination of the magnetic potential energy stored by the inductor and the electric potential energy stored by the capacitor is what's going to allow for the unique properties of the circuit, that it oscillates in time. But to see that, let's use Kirchhoff's voltage law to come up with an equation that would allow us to determine that the charge on the plates of the capacitors alternate indeed periodically. Remember that Kirchhoff's loop law says in a closed loop, the sum of the potential differences is equal to 0. Let's define the loop that we're going to analyze, which is pretty simple. Let's analyze this loop in the counterclockwise direction. So in analyzing this loop in the counterclockwise direction, let's sum up the voltages across the capacitor and across the inductor. So this would essentially be starting at point A and ending at point A. So the potential difference from A to A is equal to the potential difference from A to B plus the potential difference from B to A, and according to Kirchhoff's voltage law, this is going to sum to 0. Now notice that the potential difference from A to B is just the potential difference across the capacitor. And we know the relationship between voltage, charge, and capacitance. And that relationship says the potential difference across the capacitor is equal to the charge on the capacitor's plates divided by the capacitance. Now, since the charge on the capacitor's plates is going to vary in time because charge is being removed to drive the current, I'm going to indicate this charge as being a function of time. The potential difference across the inductor is the potential difference from B to A. This is equal to the self-induced EMF of the inductor, and as we've seen previously, this self-induced EMF is equal to minus the inductance of the inductor times the time rate of change of current through the inductor. Well, the potential difference across the inductor is minus L times the time rate of change of current, and we previously established that current is equal to minus the time rate of change of charge, based off of the charge removed from the capacitor's plates. This means that the potential difference across the inductor is equal to the product of the inductance and the second derivative of charge with respect to time. And again, we know that the charge will vary as a function of time. So now we have two expressions. We have the expression for the potential difference across the capacitor's plates. We have an expression for the potential difference across the inductor. Let's use those two expressions to determine the equation that governs the behavior of this LC circuit. We'll just put our work over here. So what we're going to do is we're going to add equations 1 and 2 together because they come from our Kirchhoff's voltage law equation. So when we add equations 1 and 2, we have the charge on the capacitor's plates as a function of time over the capacitance of the capacitor, plus the potential difference across the inductor, which is the inductance of the inductor times the second derivative of charge with respect to time, and that is equal to 0. Let's divide both sides of this equation by the inductance, and let's reorder the terms of this equation. When we do that, we get the second derivative of charge with respect to time plus 1 over the product of the inductance and the capacitance times time is equal to 0. And let's not forget that time is the independent variable in which charge is a function of. So here, this equation is the equation that Kirchhoff's voltage law gives us. But let's do another thing. For simplicity, let's take this term right here, 1 divided by the product of the inductance and the capacitance, and define it to be omega squared. In doing that, we have a second-order linear homogeneous differential equation that we should recognize from work we've done before. This equation right here is the equation that governs the behavior of LC circuits. If you recognize this second-order linear homogeneous differential equation, or at least if it looks familiar, it's because you've seen it before. This equation is identical in form to the equation of a spring block system. Let's remind ourselves of spring block systems, because the analogy between the two will help us understand how LC circuits behave. Remember, with the spring block system, we had an ideal spring attached to a block of mass m, and let's say this block is free to slide along this surface. Now this spring, if the spring is stretched or compressed, it will exert an elastic force on the block. And that elastic force is given as minus the elastic constant times the displacement along the x-axis. So let's define an x-axis to be an axis based off of the equilibrium position of the spring. So x equals 0 will correspond to the equilibrium position of the spring. Here's the positive x-axis. This spring is displaced a distance of x. We know from Newton's second law for this mass, that when we sum all of the forces along the x-axis, the result will be equal to the product of the block's mass and its acceleration in the x direction. Well, in the absence of friction and other forces, we have only one force along the x-axis, and that is the elastic force due to the spring. So taking Newton's second law and rearranging, we get the product of the mass and acceleration minus the spring's elastic force is equal to 0. Now remember, acceleration is the second derivative of position. And the elastic force is given by Hooke's law being equal to minus kx, and this is equal to 0. If we divide each term by the mass of the block and simplify, we have an expression that is the expression that we generated when we first explored spring block systems. And back then, we called this term in front of the x the angular frequency, and we defined it similar as we're defining it here. So we end up with a second-order linear homogeneous differential equation in this form. And notice that these two equations, the equation for the spring block system and the equation for the LC circuit, are identical. What that means is identical equations have identical behaviors. So if the spring block system, oscillates, and that oscillation of the spring block system, when we solve this second-order linear homogeneous differential equation, we ended up with an equation that governed the oscillations, that the displacement is equal to the amplitude of motion times the cosine of that omega term, which now we see why we called it omega, because it corresponds to angular frequency times time. This solution is periodic in time. It's cosinusoidal. It varies periodically. And what this says is that the block oscillates in time. Well, this equation that governs the spring block system is identical to the equation that governs the charge in an LC circuit. So what that must mean is that the solution for charge as a function of time in our LC circuit must have a solution identical to our spring block system. And that solution is equal to the amplitude of the charge, which is the charge we started off with at time t equals 0, times the cosine of the product of the angular frequency and time. Remember, identical equations have identical solutions. So we now have the solution for the charge on the capacitor's plates. And notice what is very, very interesting about this solution. It is a periodic function of time. That means that the charge varies periodically on the plates of the capacitor. So charge on the capacitor varies as a function of time. That means the charge on the capacitor's plates oscillates. If the charge on the capacitor's plates oscillates, that means the positive charges start on the upper plate, it circulates around to the negative plate, then once all the charge is accumulated on the negative plate, it goes back to the positive plate, then it goes back to the negative plate, then it goes back to the positive plate in a periodic fashion. If we are to plot the charge on the capacitor's plates as a function of time, we start off with our initial charge of Q naught. And this charge varies on that upper plate. So let's label this as the upper plate because that's what we're keeping track of. That charge starts off as at a maximum. Then it goes down to 0. Then it goes to a minimum. Then it goes back up. Then it goes back down. And it varies periodically forever in the absence of any electrical resistance. So we know how the charge on the capacitor plates oscillates. Well, if the charge oscillates, that means the current in our circuit will oscillate too. So that means the current will go around counterclockwise through the inductor until it comes to 0 when the capacitor is fully recharged. Then it'll oscillate back around to the upper plate. Then it'll oscillate back around and back around periodically. And we could look at that because remember, current is equal to minus the time rate of change of charge in our LC circuit. And that's the charge again on the upper plate. And since we know that charge is equal to the amplitude of charge cosine of omega t, when we evaluate this derivative, we get that current varies as a function of time as well. And that variation is equal to the product of the angular frequency and the initial charge on the capacitor plates, sine of the product of the angular frequency and time. Here is our expression for the time rate of change of charge on the capacitor's plates. And notice something. This coefficient in front of the sine term, that just corresponds to the maximum value of current, which I'll label as Imax. And so we have the amplitude of current, Imax, is equal to, or we're defining it as, the product of the angular frequency and the initial charge on the capacitor's plates. And this is a sine function. Remember, sine and cosine are out of phase by 90 degrees. Let's add this current to our graph. So the scale isn't going to be the same, but I'll just put I on the vertical axis, and we will just say that Imax is here, and again, the scale is not necessarily the same on these two. We're just drawing them on the same axis for illustrative purposes. So notice how the charge varies as cosine, while the current varies as sine. So notice how they are out of phase by 90 degrees. What this means is when charge is at a maximum on the capacitor plates, there is zero current in the circuit. And then as the charge on the upper plate decreases, notice that the current in the circuit increases. And as the charge on the capacitor's plates goes to zero, we have a maximum value of current. And then as the charge from the capacitor's plate and the upper plate starts accumulating negative charge, notice how the current in the circuit reverses direction. And then when the charge on the capacitor's plate starts accumulating positive charge again, the current begins to increase until it's eventually positive. And this behavior continues forever in the absence of resistive forces. It's an oscillation. It is a harmonic oscillation, and it is this behavior of LC circuits that allows us to listen to messages on our cell phone. It allows us to navigate with GPS. It allows us to even tune into a radio station. From our equations, we know what the angular frequency of oscillations are. Remember when we defined omega squared is equal to 1 over the product of the inductance and the capacitance? That was because equations in this form that we found before, we know that that coefficient in front of charge is the square of the angular frequency. So angular frequency is equal to 1 over the square root of the product of the inductance and the capacitance.